Okay, so today we're going to do a little bit more practice with limiting reactants, and we're now going to account for percent yield within our limiting reactant problem. So I gave you the balanced chemical formula here. Okay, so go ahead and get that written down, and then we're going to look at our problem here. Okay, it says if 0.42 grams of NH3 reacts with 0.68 grams of oxygen gas, which is O2, what's my limiting reactant? So that'll be the first part that we'll solve for. Then it tells us if the reaction only yields 78% of what it should have, what was the actual yield. So we're going to do a couple different things here, first of which has to start with our limiting reactant, finding our limiting reactant. Okay, so our two reactants are NH3 and O2, and we were given starting amounts for both of those. We can't determine which is the limiting reactant by just looking at which of our starting amounts is smaller, right? We have to take into account the fact that they don't weigh the same thing, and if our starting amounts are not given in moles, we can't judge them because we have a mole ratio and all that kind of stuff. So there's no way for us to determine absolutely which is the limiting reactant without doing the math. Okay, so we have to do our T-charts to help us find our limiting reactant. So we're going to start by doing both of our T-charts. We're going to start with what we know. So 0.42 grams of NH3. And in our T-chart, we want to go to one of our products, and we have to be consistent to which product we picked. But in this problem, we know that we want to look at the percent yield of water. So it makes the most sense for us to just do the math the first time going to water. Right? We could find our limiting reactant by going to NO, but there's really no reason to do that, right? We're going to have to answer a question about water later in the question anyway, so we might as well just save ourselves some time and we'll go to water. Okay, so we want to find out basically how many grams of water can be formed. Right? That's our goal. So we need to go from grams of NH3 to moles of NH3. Okay, and here moles gets the 1, so our mass of NH3 is 17, I believe. Okay, and now we're done with grams of NH3, so that can cancel. Right now we would be in moles of NH3, which is not our final goal. Our final goal is to be in grams of water. So next I want to get rid of moles of NH3 and go to moles of water. And this right here is called our mole ratio step. Okay, and we get the numbers for this part of our T-chart from our balanced reaction. Okay, so 4 moles and 6 moles. Okay, those numbers come directly from our balanced chemical formula. Okay, that's that mole ratio step. That is the only part of our T-chart that we can have 2 different compounds in the same column. Okay, so we're done with moles of NH3. Now we want to go from moles of water to grams of water. Okay, moles here gets the 1. The molar mass of water itself, go ahead and calculate that. Okay, we should get about 18. So now we make sure all of our units cancel the way they should have. We're done with grams. We're done with grams. We're done with moles and moles and moles and moles. We're left with grams of H2O, which is exactly what we wanted. Okay, so we're going to do the math here by multiplying across the whole top, divide by the whole bottom. Okay, so go ahead and get that plugged in. Okay, so I had my final answer at 0.667, around 0.67 grams of H2O. Okay, so that's one option, right? If NH3 is our limiting reactant, that means we could form 0.66 grams of water. Okay, now we need to see if oxygen yields something different. Okay, so oxygen, we're going to start with what we know. 0.68 grams of O2. we want to go from grams of oxygen to moles of oxygen. So grams goes on the bottom. Moles gets the 1. The molar mass of O2, be careful here, you're not just using O, is 32 grams. So we've canceled grams. You want to go from moles of O2 to moles of water. Right, we need to be consistent in terms of what we go to for our final product. So again, these numbers come directly from our balanced chemical formula. Okay, so 5 and 6 here. And then I want to go from moles of water to grams of water. Okay, so now I'll do the math. Make sure all of my units cancel properly, which I think they do. I'm done with grams, I'm done with moles of oxygen, I'm done with moles of water, and I'm left in grams of H2O, which is what I want. So go ahead and do that math. And I got about 0.459 grams of water. Okay, so of these two options, which of those yields a smaller amount of water? Right, this is smaller, 0.459. This is a smaller amount of water that yields, right, or that comes out. So that means we go back to the beginning of our T-chart and we say that O2 is our limiting reactant. Right? Oxygen gas is going to run out first. So there's no way with these two starting amounts we would ever be able to make that much water. Right? We don't have enough of our starting amounts. We don't have enough of our reactants. Oxygen would run out before that point. So the maximum amount of water that we could produce is 0.459 grams. So that answers the first part of our question. What is my limiting reactant? It's O2. The second part, it just talks about percent yield now. Okay, so I'm going to clear this screen off. So if you need to pause for a second to get some things written down, we're going to look at our percent yield now. Okay, we know that our theoretical yield always comes from our T-chart. So our theoretical yield comes from our T-chart. Our theoretical yield of water is 0.459. Okay, so knowing what we know about percent yield, our percent yield is always our actual over our theoretical yield. And this always comes from our T-chart. Right? This is what actually happens in a lab setting. Okay? So here it tells us we had a 78% yield. When we go to plug this in, we don't use it as 78%, right? We have to convert that to a decimal. So we'd say 0.78, which is the same as 78%, equals actual over theoretical, which our theoretical yield from our T-chart there was 0.459 grams of water. So to solve for our actual yield here, we need to get A by itself, right? So we just multiply these two together. So we'd say 0.78 times 0.459, and that means our actual yield was 0.358 grams of water. Okay, so that means in the lab setting, when we tested it, we only got out 78% of what we should have had, and that means our actual yield was 0.358 grams. Okay, so again here I gave you the balanced formula. This is a combustion reaction, right? We start with a hydrocarbon of some kind, has to be plus oxygen gas, and the products of a combustion reaction are always carbon dioxide and water, right? So if we're looking for types of reactions, anytime we have carbon dioxide and water in our products, right, that's going to be a sign that it's a combustion reaction. Okay. This asks us if 20 grams combust with 50 grams of oxygen gas, what is the greatest mass of water that could be formed? We want to find out how much water, and it says mass specifically, so that means we're looking for how many grams of water could we yield. Okay, then it goes on to say if 6.23 grams of water are actually formed, what is the percent yield? Okay, so we're going to do a couple things just like we did in the last problem. The first of which is going to be to start by finding the limiting reactant. So I want you to pause the video right here and start solving the limiting reactant. Once you think you're done, then you can hit play and watch and see if your answers are correct. Okay, so hit pause now and get that started. Okay, so that's what I had for my possible mass of water based on the hydrocarbon. Now I'm going to move on to finding mass based on the amount of oxygen gas given. So based on these two values of possibilities for water, the smaller value would lead us back to our limiting reactant. Okay, and the smaller amount of product that could be formed is this, 8.57, which leads us back to see that C6H6O3 is our limiting reactant. Okay, so our limiting reactant equals C6H6O3 because it yields, or it results in, a smaller amount of product that can be formed. Okay, the second part of our question asks if 6.23 grams of water are actually formed, what's the percent yield? So that means if we look at percent yield, it means percentage equals actual over theoretical. The actual yield was given to us, 6.23 grams. The theoretical yield always comes from our T-chart, and more specifically, it has to come from the T-chart of our limiting reactant. You can't just pick which one of these is your theoretical yield, right? It has to be this 8.57 because it comes from our limiting reactant T-chart. So 8.57 grams, we're going to do that math, and we get 0.73, which translates to 73% yield. Okay, so we've got our percent yield and our limiting reactant picked out. We're going to take this now one step further, and we're going to look at this question, right? This is the same thing we just solved. We solved that we know this is our limiting reactant. It said, what is the greatest mass of water that can be formed? We solved our percent yield. Now it asked how much of each product could be formed. Each product means we want to know the number of grams of hydrogen and the number of grams of carbon dioxide. The good news for us is that we already solved the number of grams. We already found how many grams of water that could be formed. And we did that based on the fact that we found our limiting reactants, and now we know since this hydrocarbon was our limiting reactant, we know that it produced 8.57 grams of water, right? That's already half of this question that's been answered. We've already answered half that question because we know each of those, we know the mass of water that's formed just from that last T-chart. We would not say that 14.06 grams of water could be formed, right? That's not one of our possibilities because we would never be able to get to that amount, right? This compound would run out before we'd have enough to make 14 grams of water, so that would not be an option. Okay, to find the mass of our other product that can be formed, we have to do another T-chart, right? And we'll go from our starting amount of our limiting reactant to our other product. Right? So we already answered one of these questions. We don't have to do the T-chart for that. But we do need to go from grams of our limiting reactant to grams of CO2. Okay, so we're going to go from grams of our hydrocarbon, C6H6O3, to moles of our hydrocarbon. And we already know the molar mass of that is 126. Now here's our mole ratio step. We're going this time to moles of CO2 because that's the other product. These numbers come directly from our balanced formula. Okay, then we want to go from moles of CO2 to grams of CO2. Okay, and the molar mass of CO2 would go right here. So we'll calculate that to come out at about 44 grams. Okay, so now we've canceled grams, we've canceled moles of carbon dioxide, and we're left with grams of carbon dioxide, which is exactly what we want. So we're going to do the math, multiply across the whole top, divide by the whole bottom, and I got about 41.9 grams of CO2. Okay, so here's one answer, and here is the other product. We would never need to do a T-chart, from oxygen gas to CO2 because oxygen gas is not our limiting reactant. So it's not going to run out first. So once we've determined what our limiting reactant is, C6H6O3, all of our T-charts should start with that. Once we've determined what our limiting reactant is, everything should stem from that starting amount and that compound from that point forward. Okay, so our final answer, this 8.57, we got that from finding our limiting reactant. Our 41.9 we found from going from our limiting reactant to our second product. Okay, so that is how you find the mass of each product that's been formed.